This video is for The Living Earth, Unit 1.2, Newton's Laws. Today's essential question is, how do forces affect the motion of objects? Hello, baby birds. Today, we begin exploring Newton's second law of motion, which is an incredibly powerful idea that helps us understand how things move and why. You've probably seen clips of the World's Strongest Man competition. In one event, a competitor straps himself to a massive semi-truck and pulls with all his might. Despite his unbelievable strength, the truck barely begins to roll. Why? This is a perfect example of Newton's second law in action. Newton realized that acceleration, which is the rate at which something speeds up or changes direction, is caused by force. But that's not the full story. Acceleration also depends on how massive the object is. A massive truck resists change in motion much more than, say, a bicycle will. In today's lesson, we'll unpack how forces, mass, and acceleration are mathematically and conceptually related. Let's begin by reviewing what a force is. A force is simply a push or a pull. When you lift a backpack off the ground, your muscles apply an upward force. If that force is greater than the force of gravity, which is pulling the backpack down, the backpack moves upward, which means its motion changes. This change happens only when the forces are unbalanced. If the force of gravity pulling down exactly equals your upward pull, the backpack won't move. But once your pull is stronger, motion occurs, meaning the object accelerates in the direction of the net force. Newton discovered something revolutionary. Applying a force causes acceleration. In other words, if something's speed is changing or it's changing its direction, then a force is acting on it. The bigger the force, the greater the acceleration. If you double the force, the acceleration also doubles, assuming that the mass stays the same. And here's the key idea. Acceleration always happens in the direction of the net force. If you push a sled to the right, it doesn't move up or down, it moves to the right in the same direction as your push. Now, imagine our strong man again. He leans forward into the harness and pulls, exerting hundreds of newtons of force. The massive semi-truck begins to move forward, not sideways or upward, because the net force is directly forward. We use the word acceleration all the time, often thinking it only means speeding up. But in physics, acceleration means any change in velocity. That could be speeding up, like it's normally used, but it could also mean slowing down or even changing direction. If our strong man gets the truck rolling from a complete stop, that is acceleration. Even if the truck's speed increases by just 0.1 meters per second every second, that's still accelerating. So, anytime an object's speed changes or it turns, even while staying at the same speed, it is accelerating. Again, here's a common mistake, thinking that a single force always causes motion, but in reality, it's multiple forces usually acting on an object at the same time. Again, think about our strong man. He's pulling forward, but like on the screen you see here, that plane that he is pulling is heavy. The tires experience friction from the road, and gravity pulls it down, while the ground pushes up. So, what determines the truck's acceleration? It turns out it's the net force, which is the sum of all of the forces acting on it. Only the net force, not any single force, determines how the object accelerates. If forces cancel out, then there's no acceleration. If they don't cancel out, the object accelerates in the direction of the leftover or net force. Remember, force is a vector, which means direction matters. Forces in the same direction add up. Forces in opposite directions subtract. Say that a strong man pulls forward with 250 newtons, but friction pushes back with 30 newtons. We might ask, what's the net force? Well, because they are moving in opposite directions, the difference between the two forces is the net force. So in this case, net force is equal to 250 newtons subtract 30 newtons, which is equal to 220 newtons. This 220 newtons is the actual force that changes the plane's motion. It is what determines the acceleration. So always pay attention to the direction when combining forces. Sample problem time. Two men push a bobsled with a total force of 250 newtons. The combined mass of the men and the bobsled is 230 kilograms. Ignoring friction, what is the acceleration of the bobsled? Here's the heart of Newton's second law, expressed as an equation. F is equal to ma. Force equals mass times acceleration. This equation tells us that more mass is equal to more force needed for the same acceleration, and that more force equals more acceleration as long as mass stays the same. Now, we can rearrange this equation to solve for acceleration, so that acceleration is equal to the net force divided by the mass. So, this lets us calculate acceleration directly, as long as we know the net force and the object's mass. Let's remember our units. Force is in newtons, represented by capital N. Mass is in kilograms, represented by kg. Acceleration is in meters per second squared. Also, since force and acceleration are vectors, we must keep track of their direction when we are problem solving. Now, let's see how mass affects acceleration. If you apply the same force to two different objects, one light and one heavy, which accelerates more? The lighter object, of course. Let's say that our strong man pulls with a force of 250 newtons. If the object's mass is 125 kilograms, it accelerates at 2 meters per second squared. But if the object is 500 kilograms, acceleration drops to just 0.5 meters per second squared. This idea shows us that acceleration is inversely proportional to mass. So that means if you double the mass, you have the acceleration. If you triple the mass, you 1/3 the acceleration. That's why the strong man can pull a plane and still have it barely move. This plane's huge mass resists acceleration, even with the tremendous force of the athlete. Newton's second law isn't just for competitions, it's everywhere. For example, your smartphone uses an accelerometer to detect motion when you tilt it or shake it. In sports, a baseball flies farther than a football when hit or thrown with the same force because it has less mass than the football. In the classroom, a small toy car accelerates more quickly when let down a ramp compared to a heavier one, as long as the same force is applied. Whenever you're playing a game, driving a car, or rolling a toy down a ramp, this law is always in effect. So let's wrap up by summarizing everything that we've learned today about Newton's second law. The big idea is that force, mass, and acceleration are all related. Specifically, Newton's second law tells us that the net force acting on an object is equal to its mass times its acceleration. This is captured in the formula F is equal to ma. From this equation, we can draw a few key conclusions, like more force means more acceleration, as long as the mass stays the same. For example, pushing harder on a cart will make it speed up faster. Also, more mass means less acceleration, assuming that the force stays the same. That's why our strongman pulling a truck or a plane accelerates slowly, even though he's applying a massive force. The truck or the plane's huge mass resists any change in motion. Then, acceleration always happens in the direction of the net force. If the net force is forward, the object accelerates forward. If the net force is upward, the object accelerates upward. All of this means that if you want to understand how something will move, you need to think carefully about the total force acting on it, the object's mass, as well as the direction of the force. Also, keep an eye out for real-life examples of Newton's second law in your daily life. Think about why heavier objects are harder to move, or how changing the way you apply force, like pushing with your legs versus your arms, can affect the motion of what you are trying to move. At this point, you should be able to generate a full and appropriate response to today's essential question. How do forces affect the motion of objects?